Unit 3, Worksheet 4, Interpreting Graphs of Accelerated Motion. Part C, find the displacement from a time of 2 seconds to a time of 8 seconds. So on this position versus time graph, I'm going to be looking at the change in position, or the displacement, from 2 seconds to 8 seconds. So our change in position, the triangle is a Greek letter delta, meaning change. The x is the symbol we use for position, is equal to our final position minus our initial position. For this region, our final position is the position at 8 seconds, and we subtract that from the position at our initial time, which here would be 2 seconds. My position at 2 seconds is going to be 24 meters. So that's what I'm going to write down over in place of the x2. And my position at 8 seconds is going to be 9 meters. So if I start off at 24 meters and I end up at 9 meters, that means that I would have decreased my position by 15 meters. So my change in position in this region is negative 15 meters, and that is going to be the displacement. For part D, we need to find the average velocity from a time of 2 seconds to a time of 8 seconds. So our average velocity, we're looking at that same time interval. But when we calculate an average velocity, it's going to be a change in position over a change in time, or the displacement over that time interval. Our change in position is 9 meters minus 24 meters, just like we did for the previous part. And our change in time is 8 seconds minus 2 seconds. So that change in position, same as our displacement, negative 15 meters, and that occurred over a time interval of 6 seconds. So the average velocity from 2 to 8 seconds is going to be negative 2.5 meters for each second. Now that's going to be something that we can look at by just drawing a line from 2 to 8. The slope of that line is the average velocity within that region, and on average, the velocity in that region is negative 2.5 meters per second. Now the slope of a position time graph does tell us the velocity, but if we actually look at the curve that was provided for us, that slope does not correspond with every single point within that region. It's just the velocity on average. We can see that by looking at part E, where we're going to try to find the instantaneous velocity at a time of 2 seconds and at a time of 8 seconds. So when we're trying to do that, if we want to look at the instantaneous velocity at a time of 2 seconds, we can end up doing the same thing where we're looking at the change in position and the change in time for the slope at 2 seconds. However, one of the problems with this is it's really hard for us to end up finding what the slope of that specific point is. Now we can try to eyeball the tangent line, which is that line that touches the curve at a single point, but we don't necessarily know if that is going to be the actual line that we need to have. So instead, we can approximate that by using a secant, which is a line that touches a curve at 2 points. So the secant that I'm going to draw is the one going from 1 second to 3 seconds. Because if I use that as my straight line, that is going to be, well, I can figure out the average velocity from 1 to 3 seconds by looking at the slope of that line. And that will correspond reasonably well with the middle time that I have in that region. Now, 2 seconds is directly in the middle of 1 to 3, so we can use that as a really good approximation of the velocity at 2 seconds. So, if my change in time is 3 seconds minus 1 second, the position at 3 seconds would be just shy of 23, but I'm going to round up to 23 just to make it easier for me. 23 meters. And my position at a time of 1 second is just shy of 25 meters. So I'm going to use that as well. So my average velocity from 1 to 3 seconds, or the velocity at 2 seconds, is going to be decreasing 2 meters over a time of 2 seconds. So that will be negative 1 meters per second for my instantaneous velocity at 2 seconds. If I'm trying to find my instantaneous velocity at 8 seconds, I can do the same thing, but I just use the slope of the secant from 7 to 9. So 9 seconds minus 7 seconds, the position at 9 seconds is 5 meters, and the position at 7 seconds is 13 meters. So here we decrease the position by 8 meters, and that occurs over a time of 2 seconds. So our instantaneous velocity at 8 seconds should be negative 4 meters per second. Now for part F, when we're trying to determine the average acceleration from a time of 2 seconds to a time of 8 seconds, we can use our equation for acceleration, which is the change in velocity. I'm going to redraw that to make that actually look like a V. Change in velocity over our change in time. So we have our times here, 8 seconds and 2 seconds. The velocity at 8 seconds we said was negative 4 meters per second. And the velocity at 2 seconds was negative 1 meter per second. So our change in velocity here would be negative 3 meters per second. So we decreased our velocity by 3 meters per second, and that occurred over a time interval of 6 seconds. So our average acceleration would be negative 0.5 meters per second each second. We got that by looking at the change in velocity from those two that we had previously calculated. The instantaneous velocity at 2 seconds was negative 1 meter per second, and the instantaneous velocity at 8 seconds was negative 4 meters per second. Now that we know the acceleration, we can actually use that for a different way to find the instantaneous velocity at 5 seconds. Now, while we could keep drawing the secants to get the instantaneous velocity at 5 seconds, we can also ultimately end up using one of our kinematic equations. Our velocity at any instant is equal to the acceleration times the time the object is accelerating for, plus its starting velocity. Now I'm going to make the assumption here that we start off from a velocity of 0 meters per second, because to me it looks like we start off with a slope of 0. So our instantaneous velocity at 0 seconds, we can assume, is going to be 0 meters per second. Our velocity at 5 seconds is then negative 0.5 meters per second squared times 5 seconds. Negative 0.5 meters per second squared times 5 seconds is going to be negative 2.5 meters per second, plus our starting velocity of 0 meters per second gives us the velocity at 5 seconds of negative 2.5 meters per second. So at this point, our slope should be negative 2.5 meters per second, which if we were to look at the average velocity from 2 to 8, we also said that was negative 2.5 meters per second, and that would correspond with our velocity at exactly 5 seconds, which is the middle time, of negative 2.5 meters per second.